If you're stuck for your trigonometry exam, I'm going to help you in full, unedited detail today on High Peak Education. What's going on, everybody? I hope that you're having a great day. Some of my most popular videos have been a full final exam review, and so today I need to take this placement exam for a company that I work with, so I might as well just record myself. I've got 20 questions, and I'm going to show you the full solutions to all these trigonometry problems today. So let's get it started right now. Okay, so here we have question 1. Given triangle ABC with angle alpha 97 degrees, gamma 25 degrees, and lowercase a equal to 21.5. Find the values of sides B and C rounded to 1 decimal place. So the convention, whenever we're solving a triangle and we have known angles and known sides, especially using trigonometry, is we want to set up the triangle in such a way that this is not necessarily a right triangle, so we won't use right triangle trigonometry. And then angle A is across from lowercase a, angle capital B is across from lowercase b, and angle capital C is across from lowercase c. Now that's true in terms of the most common convention. Here they're using alpha, then the second angle should be beta, and then we need gamma. So alpha, beta, gamma in that order would be across from or opposite from sides A, B, and C correspondingly. So let's go ahead and do our best to sketch this triangle. I sketched angle alpha here to be a little bit larger than 90 degrees, so about 97 degrees. Angle gamma is down here. This looks like a small angle. It's only 25 degrees. And then we're looking for sides B and C, which are across from beta angle and then gamma angle. Side length A is labeled across from angle alpha, and that's the only known side length. Notice, I think in order to find the other side lengths at least quickly, we probably want to find beta. Now hopefully you remember, the sum of all the interior angles for any triangle, this just comes from geometry, is 180 degrees. So let us take 180 degrees minus 97 degrees minus 25 degrees, and then we should come up with angle beta. So we'll write down this calculation right here, and then let's perform the calculation in the calculator. So 180 degrees minus 97 degrees minus 25 degrees, that looks like it should be 58 degrees. So let's write this down. Okay, so 58 degrees for angle beta. Now the reason we need that is because we're going to use the law of sines. Why the law of sines? Because we have more angles than sides, and we have a known side across from a known angle, which suggests the law of sines. So the law of sines has to do with ratios of the sine of an angle to the side length. Let's go ahead and write that formula down, especially first for finding side length B from angle beta. Okay, so it's sine alpha over A equals sine beta over B. We can go ahead and put the numbers into those expressions because we only don't have side length B. Okay, so now that the known values are substituted in, let us cross multiply and then get to solving for angle B. So if we cross multiply, we get B sine 97 degrees is equal to 21.5 sine 58 degrees. All right, to get side length B, we need to divide by the sine of 97 degrees, which is just a decimal. So let's go ahead and get B solved for. So that's 21.5 sine 58 degrees divided by sine of 97 degrees. We can perform this in the calculator. Be sure to have your calculator in degree mode. Okay, so using our calculator with trigonometric functions, I'm going to use this alpha fraction bar, and I'm going to do 21.5 times the sine of 58, and then I'm going to divide that by, I'm going to divide that by the sine of 97, assuming these are in degrees for the angles. So we get about 18.37. So with B being about 18.4, we should cross out 2 of the answer choices. So we're down to the first and the last choice. And to perform this calculation, let's go ahead and just do the law of sines again, but this time with angle gamma and side length C. Okay, so here's the law of sines with angle gamma and side length C. and it's going to work itself out very, very similarly to before. Main real difference is that we're going to use angle gamma, and the denominator is c, not b, so we're using now sine of 25 degrees over c. Cross multiply again, so we have c sine 97 degrees equals 21.5 sine 25 degrees. Notice we usually put the lengths in front of the trig functions, because we want to put it towards the back of the parentheses, because that could get confused with the angle. So let's divide, and then we'll be able to have the expression for side length c. Okay, so side length c is 21.5 sine 25 degrees divided by sine of 97 degrees. So a little trick, you can use the arrow up on the TI-84 and then re-put the same calculation in your calculator. But notice, I only really need to change the angle inside the sign of the numerator, change that to 25, because the rest, as you can see, is exactly the same. So we get 9.2 or so for side length c. So there we have it. So 9.2 for side length c. So this is going to be the first choice. Okay, so on question number 2 here, approximate to the nearest 0.01 radians, that is 100th of a radian, all angles theta in the interval 0 to 2 pi. 2 pi, notice we don't include the right-hand endpoint, only the 0 left-hand endpoint is included, that satisfy the equation sine of theta equals negative 0.5792. So let's think about how this works. First of all, because we're in the interval 0 to 2 pi, we want to make sure that any angles of interest fall in that range. Furthermore, when we go to solve for theta, we're going to introduce inverse sines, sometimes called arc sine. So now we have theta is equal to arc sine, or inverse sine, of negative 0.5792. Now, negative 0.5792 is the ratio. In other words, it's not the angle, it's the ratio of the opposite side to the hypotenuse, because that's the SOHCAHTOA rule. Hopefully you know that the angle theta will have a negative sign value in both quadrant 3 and quadrant 4. In other words, we're going to have two answers to this problem, as we can see here, in one of the answer choices. Now, it could be none of the above, but it's likely going to be two answer choices. And the reference angle must be that which comes out of this angle theta. Now, let's be really clear. Hopefully you know that as it relates to inverse sine in terms of the calculator is only defined in quadrants 1 and 4. Given it's defined in quadrant 4, we're going to pick up a negative angle here. But that negative angle, we're going to take the absolute value of it, and we're going to make that into our reference angle. I think this will become clearer as we do the calculation and we sketch out the two triangles, one of which is in quadrant 3, the other is quadrant 4, having that same reference angle. So let's perform the calculation on the calculator. Also, on this exam, you're going to have to switch your calculator between degree and radian mode several times. So we're going to make sure we're in radian mode. Okay, so switching the calculator here over to radian mode, let's go ahead and do this calculation. Let's go second sine, that's inverse sine, of negative 0.5792. Okay, so theta is about negative 0.6185 radians. Let's discuss why we know this is in quadrant 4. Because quadrant 4 has radian angles between 0 and about negative 1.57 radians. Because negative 1.57 radians is at the bottom of the unit circle. It's namely at negative pi over 2. Because pi is about 3.14. And about half of that is about 1.57. So what that means is if I draw a basic axis here, we could sketch that this is our angle theta. And notice it's rotated this way because it's rotated clockwise, which is in the negative direction, with the positive x-axis to the right, the positive y-axis upward, the negative y-axis down here. This is quadrant 4. Now, to get the reference angle, what we need to do is we need to go ahead and take the absolute value of this angle in radians and form right triangles. So let me explain. So as I mentioned before, we're going to focus in on quadrants 3 and 4. And notice I'm doing my best to come up with congruent right triangles having the same reference angle, So this right here is theta r, r meaning reference, and theta r, so theta r, theta reference is 0.1685. And so that's what we need for our reference angle. But notice that means we're going to get two standard angles. That is angles in standard position rotated counterclockwise from the positive x-axis to get our two answers. Our first standard angle will be rotated from the positive x-axis this way with the terminal side in quadrant 3. So that's going to be this angle here. And then we need one more angle in standard position with the terminal side existing in quadrant 4. So if we draw that, what we'll have is we'll have it going all the way around here to this terminal side, and then that's now in quadrant 4. And notice that's going to be what special angles? Well, notice in quadrant 3, that's going to be pi plus the reference angle, because we went a reference angle rotation further than pi radians. And then notice in quadrant 4, we're going to go 2 pi minus the reference angle, because remember, we have to be quadrants 3 and 4, because those are the only quadrants for which sine is negative. And I took the time to label our axes. Whenever the y value is negative, that's like saying the opposite side of the right triangle is negative. So each of these right triangles being a congruent right triangle is what we need, because we need the exact same trig ratio, which is negative. The reason this doesn't give it to us is because this is a negative angle in radians for quadrant 4. We need angles only between 0 and 2 pi. Let's do this first one. Let's calculate pi plus this reference angle. So pi plus this reference angle is going to be pi plus 0.6185. Okay, so we get about 3.76 radians. So that seems to be either this one or this one, the first or the fourth choice. Then let's see if we can get the other one. So I went up here and recopied this line, but I'm going to go second insert mode, put a 2 there, it's 2 pi, and then I'm going to change out of insert mode to overwrite mode and go minus. It's 2 pi minus 0.6185 radians. And that gives us 5.665 radians. And then notice that's going to be our other angle in standard position. So 5.665 rounds to 5.67. So I think that's going to be this. So we have the first choice up here for our correct answer. Notice that's going to be the two angles in standard position, quadrant 3, quadrant 4, using that reference angle, getting us the answer to the equation for this sine value. By the way, many of these things can be confirmed with a graphing calculator or a graph like Desmos or something, but I'm not necessarily always going to show that. Okay? Hope that makes sense. Let's move on. Okay, let's have a look at number 3 here. A surveyor notes that the direction from point A to point B is N50 angle W, and the direction from A to point C is S30 degrees W. The distance from A to B is 275 yards. The distance from B to C is 450 yards. Approximate the distance from A to C to the nearest whole yard. Now, this takes a little explaining, but we really need to get understanding what this means. So this is like saying 50 degrees north of west, and then this is saying 30 degrees south of west. Now, west is towards the left on typical diagrams. In other words, towards a negative x-axis. So what I think we want to do is we want to draw quadrants 2 and 3 where the x-axis is negative, and then we're going to look from point A to point B, point A to point C, and then let's see if we can connect points B and C. Okay, so what I've got is I've got the x and y axes drawn here. Positive y up, positive x to the right, negative x to the left, negative y downward. And I'm going to call west towards the left, that's the negative x-axis. I'm going to call north in the positive y direction. I'm going to call south in the negative y direction. Then east is in the positive x direction. But I don't think a lot of things are going to be going east. Also, I'm going to set the origin, like 0, 0 here, to be point A. Because we're most interested in point A to point C, and then point A to point B. All right, so point A to point B is 50 degrees north of west. So 50 degrees north of west. So notice the way I have it set up here on my software, 270 is shown to be straight west. So if I go 50 degrees north of that, that's going to be 320 here. And point A to B is 275 yards. So let's just make it maybe that long. So this is 275 yards. Now that's up to point B here. So let's label this as point B. And again, this right here is a 50-degree angle. It's 50 degrees north, that's rotated towards the north, from straight west. Let's do the same thing from point A to point C. That is 30 degrees south of west. So 30 degrees south of west. So let's go straight west first, but let's go 30 degrees down this way. We don't know exactly, but something like that. And then this would be point C. And again, this right here is a 30-degree angle, and it's rotated this way. So it's going to be south of west. Then we're told we have the distance between point B and point C to be 450 yards. So let's connect these 2 points. And let's label this as 450 yards. Now that we have this figured out, we want to approximate the distance from A to C to the nearest whole yard. So we want this distance. So from here to here, from A to C. That's the length of the blue line. We have 2 sides of a triangle, which is not necessarily a right triangle. We have this one angle, and we have this one angle across from this side. I think we need to use either the law of sines or law of cosines. So we do need to use the law of sines, because in this case, it's going to be a little bit tricky in that I think we actually need to solve for this angle down here at C. Why? Because it's the only side we know that is across from a known side, this 275. Once we find this angle, we can quickly find this angle. So to go from angle C to angle B, it's very quick finding that. And then we can find side length D. So this is the so-called side-side angle situation. And it turns out that the reason the law of cosines is not going to work is because the law of cosines only works if you have an angle in between 2 known sides, okay, which we do not have. So let's first find angle C. So from the law of sines, and by the way, I'm going to relabel this side lowercase c, and I'm going to label lowercase a equal to 450 yards, because that's across from angle A. Okay, so we have sine A over lowercase a equals sine C over lowercase c. By the way, many of you will learn the law of sines as lowercase a over sine A, lowercase c over sine C. It means the same thing, just a reciprocal, but if you reciprocate both sides, you're going to get the same answer. So we can put the numbers in to start finding angle C. Okay, so we got sine 80 degrees, because that's 50 degrees plus 30 degrees, over 450 is equal to sine of the unknown angle C over 275 yards. Okay, so let's cross multiply. So we have 275 sine of 80 degrees equals 450 sine of angle C. Now we have to divide by 450 and then take the inverse sine of both sides to find this angle. So there's a dividing by 450. Let's take the inverse sine of both sides. Okay, so there's the inverse sine calculation. So we need to use the scientific calculator here for sure. Okay, so let us do inverse sine of, and I'm going to use this fraction bar, and I'm going to make sure it's closed off from the beginning. And I'm going to go up here to the numerator. I'm going to type in 275 sine of 80 over 450. Now, by the way, one more thing. I have to make sure my calculator is in degree mode. It was not. So let's go to degree mode, and then we're going to hit enter. So we're going to get about 37 degrees. So then what would angle B become? Well, hopefully it should make sense to you that angle B is just going to come from subtracting angle A and angle C from 180 degrees. So let's subtract 80 degrees, 37 degrees. We end up with 63 degrees. Okay, so now we have angle B. Now that we have angle B, we can go for finding side length B. Side length B is what we're interested in, because that's across from angle B. So we want to use the law of sines again. this time for angle B and side length lowercase b. So we have sine of 80 degrees over 450 is equal to the sine of 63 degrees over b. So we got to cross multiply and then divide to find our final answer. Okay, so b sine 80 degrees is equal to 450 sine 63 degrees. Let's divide by sine of 80 degrees, then put it in the calculator. So 450 times the sine of 63 degrees divided by the sine of 80 degrees. And we get about 407 yards. Now, notice that's none of the choices here. The only issue we could have had is in misinterpreting what this measurement and this measurement really means. Okay, so I've checked a couple other resources. I do believe this is correct. So we're going to go with none of the above because I believe this is how the naming convention is done. Hope that makes sense. Let's move on. Let's look at number 4. It says, find the area of the sector of a circle determined by the central angle theta that subtends an arc of length 13.8 centimeters on a circle with radius of 5.2 centimeters, round to the nearest tenth. So I'm going to find the area of this sector. Hopefully you're aware that arc length and radius can be used to find the central angle. Once we have the central angle, then as long as the central angle is in radians, we can use the formula for the area of the sector. So let's first find that angle theta in radians. So the angle theta in radians is equal to S over R. S is the arc length, R is the radius. So let's do this division. Okay, so 13.8 centimeters divided by 5.2 centimeters. Let's get this approximately in radians. So 13.8 divided by 5.2, and we're going to get about 2.654 radians or so. So this is our radian angle measure. Now, we need the area of a sector in radian measure. And the formula is going to be area equals 1/2 radius squared times theta in radians. So we have everything we need. We can go ahead and calculate this area. Okay, so 1/2 times 5.2 centimeters squared times 2.654 radians. So we're going to get about 35.88 or so square centimeters. Okay, so that's our approximate area rounded to 1 decimal place. That is the nearest tenth. We're going to have about 35.9 square centimeters for the correct answer. Hope that makes sense. Let's move on. Let's look at this problem, number 5. Complete the statement. As x approaches -3 pi over 2 from the right, so this is a positive superscript. We're going to approach -3 pi over 2 from the right. Tangent x, does it approach 1, infinity, negative infinity, undefined, or none of the above? The idea is that let us think about the graph of tangent or the unit circle. So on the unit circle, -3 pi over 2 would be at the top of the unit circle when we go clockwise, in other words, in the negative direction. Now, it turns out going this direction, we are going to go towards an infinity, so it's going to be one of these two, because tangent is indeed undefined there. But what are we going to actually approach? Well, it turns out that on this side over here, in quadrant 2, tangent was negative. But it not only was negative, it got more and more large magnitude negative. So we're going to approach negative infinity. Some of you may not be so comfortable with that explanation, knowing that tangent is negative in quadrant 2 as we approach pi over 2 at the top, positive pi over 2, or -3 pi over 2 if we go clockwise as a negative angle. Let's imagine what the graph of tangent looks like. So if you picture the graph of tangent, here is a vertical asymptote at -pi over 2. And then you have this kind of S-curve looking branch here. The next asymptote, because tangent is pi periodic, is -3 pi over 2. And once again, you have another S-curve looking thing here. So if we approach -3 pi over 2 from the right, what's happening is we're approaching this value this way. So you see we're going towards negative infinity. So we have greater confidence that we have the correct answer of negative infinity. Hope that makes sense. Let's move it on. Okay, let's look at number 6. Express the angle 200 degrees, 31 minutes, 9 seconds as a decimal to the nearest 10,000th of a degree. So what we could do is we could add this up by hand or have the calculator do it for us. But anyway, it's going to be 200, that's degrees, plus 31 minutes. So that's 31 over 60, because minutes is 60ths of an angle. And then seconds is 60ths of a minute. So this is going to be 9 to get down to the seconds. So that's going to be 60 60ths, so 3,600. Okay, because 60 times 60 is 3,600. So if we add these up and get a decimal approximation, we're going to get as close as we need to get in decimal degrees. Okay, so first 200 degrees plus 31 over 60 plus 9 over 3,600. And then let's go 4 decimal places. So this to me is like 200.5192. 5192 right there. So it looks like this is going to be our first answer choice. That's going to be our correct answer. Hope that makes sense. Let's move on. For number 7, a builder wishes to construct a ramp at an angle of 9 degrees with the horizontal to a height of 2 feet above the level ground. Approximate the length of the ramp to the nearest tenth of a foot. So let's set up a 9-degree angle with respect to horizontal. So that's right about 9 degrees. Let's get horizontal shown here. And then here's the vertical part. Now this is exactly a right triangle when we think about these 3 sides. So we have a right angle here, and then we know this is 2 feet high. This is 9 degrees. We want the length of the ramp, so we want this length L. Now notice this length L is like the hypotenuse of the right triangle, and then the 2 feet is like the height. We could call that like Y. This would be like Y. That would be the opposite side of this right triangle. So then what do we have? We have opposite and hypotenuse. So we're thinking about sine, because sine from that SOHCAHTOA formula is opposite over hypotenuse. So in this case, we would say the sine of 9 degrees is going to equal to opposite, which is 2 feet, over the length of the ramp, which is the hypotenuse. Now think about how we're going to solve this. We have to multiply both sides by L, and we have to divide by sine of 9 degrees. So we've got L sine 9 degrees is equal to 2. Let's divide by sine 9 degrees. So L is 2 divided by the sine of 9 degrees. Let's get an approximation on that. I'm going to use the calculator, making sure it's in degree mode. So it's 2 divided by the sine of 9 degrees. It's about 12.78 feet. Okay, so 12.78 feet. So let's get as close as we can. So 12.8 feet, that seems correct. All right, so we'll choose that for the correct answer, and then we'll move on. Hey, thanks for checking out High Peak Education. Do you need some one-on-one guidance? Go to our Calendly link and book a grade boost game plan. Or if you're studying for a standardized test, for a score soar game plan. At highpeakeducation.com, you can click book now or see our Calendly page. Okay, let's get back to today's video. So here's question number 8. Write the expression as an algebraic expression in x for x greater than 0. What we have is we have sine of 2 cosine of inverse of x. Let's think about how we're going to do this. Cosine inverse of x is like saying, give me the arc or give me the angle whose ratio is x, or like x over 1. But then we're going to do 2 times that, and that's going to be an angle twice that angle. At least initially, it's been a good idea to draw a right triangle to understand this. So if we draw some arbitrary right triangle, the cosine is the adjacent over the hypotenuse. So that's x over 1. X is adjacent, hypotenuse is 1. Notice x is next to this angle theta, and 1 is the hypotenuse. So what we need is we need 2 times that angle. If we're going to do 2 times that angle, what's going to happen is this is going to be 2 theta instead of theta. So you could think about this as like sine of 2 theta. But hopefully you're aware, in terms of trigonometric functions, notice it wouldn't be quite so easy to double this angle. It'd be very difficult to change the sides of the right triangle. We're not exactly sure how the sides are going to change. we can use an identity for the sine of 2 theta. Now hopefully you're aware of this, but the sine of 2 theta, it should be 2 sine theta cosine theta. Okay, so because it's 2 sine theta cosine theta, we can actually come up with all the expressions from this right triangle. But in order to do that, we have to find the opposite side using Pythagorean theorem. In order to do that, what we have to do is we have to go ahead and say hypotenuse squared minus one of the legs squared is equal to the other leg squared. So from the Pythagorean theorem, 1 squared is 1, x squared is just x squared, but then let's take the square root of that. So that means this y value will be 1 minus x squared. And that we can put on this vertical part of this right triangle. Okay, so there it is. Now we have all the sides of the right triangle and we can express 2 sine theta cosine theta. And so sine of theta is going to be square root of 1 minus x squared over 1, hypotenuse is 1, and then cosine is going to be x over 1. But then we could just rearrange these by multiplying. So I think it's going to be 2x times the square root of 1 minus x squared. So that will be exactly this fourth choice here. So that is the algebraic expression for the sine of 2 times the inverse cosine of x. Hope that makes sense. This is a combined trigonometric and inverse trigonometric problem. Let's move on. So number 9 here, it says express as a trigonometric function of one angle, cosine 48 degrees, cosine 13 degrees, minus sine 48 degrees, sine 13 degrees. This has the classic form of an angle sum or difference identity because we repeat the same angle, and you can imagine that either angle A is 48 degrees, angle B is 13 degrees. You could also call them alpha and beta. It's either going to be cosine or sine of either a sum or a difference. So let's look up our identities. So from our angle sum and difference identities, we see that which has the form cosine cosine minus sine sine, that to me looks like it's the sum of 2 angles for a cosine. So a, lowercase a, is 48 degrees, lowercase b is 13 degrees. So we need cosine of 48 degrees plus 13 degrees trigonometric function in the same angle argument. But 48 plus 13 is going to be 61 degrees. So that's exactly this answer, the cosine of 61 degrees. So that's exactly what this is because we're expressing a trigonometric function of one angle. Hope that makes sense. Let's move on. So now for question number 10, it says find cosine theta. Well, cosine is going to be the adjacent over the hypotenuse, but the adjacent side is not found yet. So we can find the adjacent side from the Pythagorean theorem using hypotenuse squared minus one of the legs squared equals this side squared. So we can then take the square root. So what you might call side A is going to be the square root of c squared minus b squared. And notice when we express the cosine, it's going to be this side, which is the A, it's the adjacent, over the hypotenuse, which is c. So it's going to be the square root of c squared minus b squared over c. And that's going to be this third choice. So that's going to be our correct answer. That's all we need to do for number 10. Let's move on. So for question number 11, an airplane is flying in the direction 165 degrees with an airspeed of 450 miles per hour with a 50 mile per hour wind blowing directly from the west. Approximate the true course of the airplane to the nearest whole degree. All right, so let's get the cardinal directions marked as it relates to navigation, typically for airplanes and ships and this kind of thing, and see how it relates to trigonometry. So I'm going to draw those coordinate axes and label them carefully. So I've drawn the cardinal directions. I've drawn the positive x, positive y, negative x, negative y. The positive x direction would be east. The positive y direction would be north. The negative x direction would be west. And the negative y direction would be south. Now notice though, in navigational degrees, typically north is 0 degrees, towards the east is 90 degrees, towards the south is 180 degrees, towards the west is 270 degrees. Also, given we know it says the wind is blowing directly from the west, winds in meteorology and atmospheric science, hopefully you've seen this on the channel before, are named in the direction from which they come. So a westerly wind blows from west to east. So it comes from the west towards the east, so it's heading in the direction of 90 degrees. So I hope that all makes sense. Now let's get into drawing some vectors for the airplane's airspeed and then also for that wind. Okay, so for the airplane, the direction is 165 degrees with an airspeed of 450 miles per hour. So let's do a nice long vector in the direction of 165. So that's mostly towards the south, but just a little bit east. So you might call it south, southeast. So maybe something like this. So let's have this represent our airplane vector. And then the wind, again, is from west to east. So it's in the 90-degree direction, the positive x direction. And then notice I'm going to make the vector quite a bit shorter because it only should be 1/9 of the length of the red vector. Now, as pictured, it's not perfect, but we're just doing the best we can. We're going to approximate the true course of the airplane to the nearest whole degree. To do that, we need to add these two vectors. So from the origin, with the airplane and the wind, this is the entire true course of the airplane. So we need to add together these two vectors. Now, adding these two vectors is the same thing as adding vector components. Turns out the wind is only in the x direction. So I didn't mark that before in blue, but the wind is 50 miles per hour in the x direction. So let's call that, you could either say 50 I hat or 50 in the x component. Okay, so again, you could write it in two ways. 50 in the x component or 50 I hat in terms of miles per hour. I'm using the subscript W for wind, and then notice it's a vector because it has magnitude and direction. It has size and orientation. Now that we have vector v wind here, let's also get a vector for vp, that is v plane. And let's think about how we're going to find the components of v plane, because it has both a positive x and a negative y component. So for v plane, what we'll do is we'll do 450 times the cosine of theta r. Theta r is the reference angle. We need to figure out what that angle is. And then we're going to go minus 450 times sine of theta r. So let's talk about how I'm getting these things. Let's draw the appropriate right triangle that goes along with the airplane. Hopefully you see what this looks like. This is the plane vector reproduced, and then what's the right triangle that goes along with it? So notice it's a right triangle that has its hypotenuse as the magnitude of the airplane's speed. So that's 450 for the hypotenuse. Notice if we set up theta r as the reference angle, notice the reference angle is the smallest angle to the positive x-axis. Now remember, we were told this is 165 degrees. So let me go ahead and label that on the diagram. So it's 165 degrees. We could call that theta. But then theta r, which is the reference angle, is how much further is this angle from 90 degrees. So we need to take 165 degrees minus 90 degrees. We'll get 75 degrees. And then notice that the cosine of this angle theta is going to be the adjacent side over the hypotenuse, but the adjacent side is the x component. So the speed of the plane in the x direction is going to be positive, but it's going to be related to the cosine because it's going to be adjacent over hypotenuse. And then the y component is going to be downward. It's going to be negative. So VPY should be a negative number as long as we're using an acute angle. An acute angle as a reference angle is an angle between 0 and 90 degrees, because if you use an angle between 0 and 90 degrees, cosine and sine should both be positive. But since we know we should end up with a negative y value for the y component, we're going to make sure we've got a minus there. The hypotenuse is 450 miles per hour, sine of 75 degrees. Okay, so this is how we get our components. So hopefully you see where all that comes from. So let's do the calculations to get the VP in the x and the y directions. That's the plane's horizontal and vertical components to its velocity. Okay, so it's 450 cosine 75 degrees, comma, negative 450 sine 75 degrees. We're going to make sure the calculator is in degree mode, do these calculations. Let's get an approximation. So we'll do 450 times the cosine of 75 degrees. And then I'm going to go arrow up, and I'm going to go change cosine to sine, and I'm going to make this a negative. So I'm going to go second, insert, negative sign. There we go. So we're going to have 116.5 miles per hour and negative 434.7 miles per hour. Okay, so now we have the approximations for the plane's velocity, x and y components. Then we need to get the total velocity by adding the x component of the wind to that of the plane to get v total. So v total, let's do in green for this analysis. Notice the plus 50 is coming from the wind, and these other two parts, of course, are coming from the plane itself. So 116.5 plus 50, I think, is going to be 166.5. Okay, so now we have the vector components of the total velocity of the airplane, and we want to approximate the true course of the airplane's heading. Now notice what we're asked to find is we're asked to find the reference angle and thus the full angle of the heading. So I'm going to call this theta RT, R for reference, T for total. And then we need to find this angle. Notice that we have the opposite side and we have the adjacent side. Because we have the y component, we have the x component. Oh, say we have v total y, v total x. So let's just use tangent and in fact inverse tangent to do this calculation. Okay, so tangent of theta reference total is v total y over v total x. So let's take the inverse tangent to get the angle itself. So this angle, inverse tangent, let's put the numbers in. So this is going to be the inverse tangent of negative 434.7 over 166.5. So let's do that in the scientific calculator. So inverse tangent of this number divided by this other number. We have these already in the calculator. I can just scroll up to those numbers, click on them, divide them, and then we can get our answer. Oh, and then notice I get negative 75, so I shouldn't actually be using 116.5 in the denominator, should I? I should actually be using 166, because remember, in the denominator, we added 50 to it in terms of the x component, so we're going to get a different angle. So you get about negative 69 degrees. So let's write that down. Okay, so that reference angle is about negative 69 degrees. Now, as rotated from north, 90 degrees plus 69 degrees to get down into the southeast quadrant, quadrant 4, at least in the traditional trig angles, that's going to be about 159 degrees, 90 plus 69. So 159 degrees would be the angle heading. So now we have the correct answer. We know that the heading of the plane, as a result of its motion, its velocity in still air, and the wind itself, is going to give a total heading, VT, at about negative 69 degrees rotated from the eastward direction, but that's a total heading of about 159 degrees. Okay, hope that makes sense. For question 11, let's move on. Use inverse trigonometric functions to find the solutions of the equation that are in the given interval and approximate the solutions to 4 decimal places. Okay, so we have 3 cosine squared x plus 4 cosine x minus 5 equals 0 on the interval from 0 to 2 pi. Now 0 has a bracket, 2 pi is a parenthesis. That's because 0 and 2 pi are coterminal angles. So if we get an answer that's 0, we report it as 0. We don't report it as 2 pi. And then what that means is within one full rotation, that is one full revolution all the way around the unit circle, in the positive angles. So in other words, angles going counterclockwise. Okay, so let's see about solving this equation. Notice it's in a quadratic form. And what I mean by quadratic form, I mean we have a cosine squared term, a cosine term, and then a constant. So we could maybe perhaps think about doing a substitution here. So a substitution might help us. Let's let u equal cosine x. U is a common letter that's used in mathematics when substituting for an entire function. Then we'll be able to see this as a quadratic even better. So we end up with 3u squared plus 4u minus 5 equals 0. Now consider, when we have this for our quadratic, we're going to solve for the values of u with quadratic solving, and then we'll substitute back in cosine x and then perform inverse cosine. Now, 3 times negative 5 is negative 15. We ask ourselves, what two numbers multiply to negative 15 but they add up to positive 4? And it turns out there's no pair of numbers that do that. So this is not a factorable quadratic. That's because b squared minus 4ac, which is the discriminant, is not equal to a perfect square. So as a result, we're going to need to use the quadratic formula. So I'm going to show my steps of the quadratic formula below, and then we'll see what the value of u is that we end up with. So the leading coefficient a is equal to 3, the middle coefficient is equal to 4, and then the final coefficient, which is the constant term, is equal to negative 5. So a is 3, b is 4, c is negative 5, and thus, hopefully you remember from the quadratic formula, it looks like this: negative b plus or minus the square root of b squared minus 4ac over 2a. Notice the discriminant, when we're going to calculate that, is equal to 76. So it's not a perfect square, so this was not factorable. So plugging our numbers in, we've got negative 4 plus or minus the square root of 4 squared minus 4 times 3 times negative 5 over 2 times 3. So we get negative 4 plus or minus the square root of 76, because that's the same thing as 16 plus 60 over 6. Now, square root of 76, let's think about this for a second. So 76 has 19 as a factor. So 19, which is a prime number, times 4 is 76. But 4 is a perfect square. So the square root of 4 is 2. So we'll end up with negative 4 plus 2 square root of 19 over 6. But 4 is even, the 2 out front is even, and 6 is even. So you can reduce this to negative 2 over 3 and plus 1/3 square root of 19, or negative 2 over 3 minus 1 over square root of 19. So you can go plus a negative 1/3, or you could just have minus and then just 1/3. So either way, we have our correct answer now for u. Then we need to substitute cosine x back in. Okay, so now we have cosine x equals negative 2 plus the square root of 19 over 3, or cosine x equals negative 2 minus the square root of 19 over 3. Part of the reason I wrote them as single combined fractions again is because I think it's going to be easier to take the inverse cosine of each of those. Okay, so that's x equals inverse cosine of negative 2 plus square root of 19 over 3, or x equals inverse cosine of negative 2 minus square root of 19 over 3. Now notice, because we're getting two different answers, and the square root of 19, now let's just think about that for a second. That's more than the square root of 16, which is a little bit more than 4. So 4 plus negative 2, that's going to give you a positive ratio here, but then clearly this is going to be a negative ratio. So we're going to have positive and negative cosine ratios. So we're really going to need two positive places on the unit circle, that's quadrants 1 and 4. And we're going to need two negative places on the unit circle. That's quadrants 2 and 3. So notice this x value here in red is going to have positive values for cosine in quadrants 1 and 4. What I've got here for the negative values of cosine are going to have angles over here in quadrant 2 and 3. Now these are congruent triangles having the same reference angle, but we need to navigate this kind of carefully. So let's do that. So for the first x, the positive x, let's use the calculator in radian mode, and then let's get that reference angle. It's going to be the same reference angle in quadrant 4. So switching the calculator into radian mode, make sure you're in radian mode. Let's go inverse cosine, and I'll use the fraction bar here, alpha fraction bar. I'm going to go negative 2 plus square root of 19 over 3, and then close parenthesis, enter. Okay, so it's about 0.666 radians. Now that is one of the possible answers. We also need a value of x here that corresponds to quadrant 4. to get the other x, that's going to be 2 pi minus 0.666. Because again, you go 2 pi radians all the way around to the positive x-axis in quadrant 4, but with that reference angle, you subtract off the 0.666 radians. So let's go 2 pi minus this angle here, and we get about 5.617 radians. Now, I'm leaning towards this answer, but that could be because even though I drew negative angle ratios here, it's very possible that this might actually be outside the domain. Let's see about that. So let me go ahead and just go back to this inverse cosine here. Let me take off the inverse cosine part and then change this to not a add, but a subtract in the numerator. And then we get negative 2.11. But remember, the range of cosine values only goes between -1 and +1. So if we have a ratio outside of -1, say like -2.1, I think we're going to get an error. So let's go ahead and see if we can verify that by doing inverse cosine. So if we do minus right there, boom, it says domain error. So these blue triangles don't actually exist for negative cosine ratios. This does not give us any solutions. So even though the quadratic gave us that as a possible solution, the trigonometry shows that it's not a solution. Okay, so hope that makes sense. These two angles are indeed the correct angle measures in radians for solving this quadratic equation, and these would be our answer. Okay, it's not going to be none of the above because it's not going to be 4 solutions. It's going to be 2 solutions. Because also a lot of times, fundamental theorem of algebra says that a quadratic of power 2, you expect 2 solutions. So I hope that makes sense. That's it for question number 12. Let's move on. Okay, so here we have for number 13, tangent squared theta times the quantity of cotangent squared theta plus 1 is equivalent to which of the following? Hopefully you're aware that cotangent is the reciprocal of tangent. So I could write this as tangent squared theta times the quantity of 1 over tangent squared theta plus 1. And then we want to use the distributive property. So let's distribute the tangent squared across both of those terms. Part of the reason we want to get it across both those terms is we see the final answer only has a single trigonometric function. We're not going to have an addition. But furthermore, tangent squared over tangent squared. When I multiply it into the first term, tangent squared over tangent squared, just the same thing over itself, that's going to equal 1. So the result is going to be 1 plus tangent squared of theta. But wait a minute, hopefully you recognize that from your Pythagorean identities. In other words, 1 plus tangent squared theta is the same thing as sine squared theta plus cosine squared theta equals 1, but you just divide it through by cosine squared. So you get 1 plus tangent squared is equal to 1 over cosine squared, which is secant squared. So indeed, this is secant squared theta, and that we will put for our correct answer. Hope that makes sense. Let's just move on. For number 14, find all solutions of the equation 2 cosine 2 theta minus square root of 3 equal to 0 when n is any arbitrary integer. So we're going to solve this equation for theta. So I think we need to isolate the cosine term first, then do inverse cosine, then make some arguments about theta. So let's first add the square root of 3 over. Okay, so we first have 2 cosine 2 theta equals square root of 3. Let's divide by 2. Okay, so we have cosine 2 theta equals square root of 3 over 2. Then we need to take inverse cosine of both sides. Remember, this ratio on the right-hand side is positive, so it's going to be quadrants 1 and 4. Okay, so we have 2 theta is equal to the inverse cosine of square root of 3 over 2. Now, once we have this, let's get a list of any arbitrary angles in terms of n that are in quadrant 1 and 4 and coterminal angles to those involving n as an arbitrary integer. Okay, so we have these right triangles drawn. Notice that one of them is in quadrant 1, the other's in quadrant 4. That is, they're both going to have the same reference angle. Now, hopefully you know this from your special angles in trigonometry. When you have inverse cosine of square root of 3 over 2, that's exactly a 30-degree angle or pi over 6 radians. So theta r, this reference angle, is pi over 6 radians, no matter if you're in quadrant 1 or 4. Now that we have that, we can deduce that the first angle, theta 1, is going to be exactly pi over 6, but then any coterminal angle with that. So you can add 2 pi, subtract 2 pi, you get the same landing position, coterminal angles. So there we go. Theta 1 is pi over 6 plus 2 pi n. Notice that the theta 2, which is in blue, is going to have the same reference angle of pi over 6, but that's going to be 11 pi over 6. So it's 11 pi over 6 plus 2 pi n, because 11 pi over 6 is pi over 6 radians shorter than 2 pi, which would be 12 pi over 6. 2 pi n, because again, 2 pi is just a full rotation, same landing spot, coterminal angle, that kind of thing. So what I should have been saying a moment ago is everything I was saying was correct, but remember what I was saying was true for 2 theta 1, or 2 times theta 2. At first, by just taking inverse cosine, we were solving for 2 theta as opposed to theta. So we need to divide each of these by 2. So to get our final answer, we need to divide each of these by 2. So pi over 6 divided by 2, and then 11 pi over 6 divided by 2 is going to give you pi over 12, 11 pi over 12, and this is going to be pi n. So after dividing by 2, we have these answers, as I said out loud a moment ago. Let's look at the answer choices. So we need pi over 12 plus pi n, and 11 pi over 12 plus pi n. Yes, that's this second choice. So this would be our answers. Hope that makes sense. Let's move on. Number 15, find all solutions to the equation in the interval 0 to 2 pi. Again, 0 with the bracket, 2 pi with the parenthesis, because if we get an answer of 0, we include the 0, not 2 pi, because those are coterminal angles, only angles that are positive, in other words, counterclockwise rotation in standard angle position. So we have cotangent of 2 theta minus pi over 3 equals square root of 3. Well, first of all, what we should do is, we don't really often do inverse trig functions of the reciprocal functions. We don't often do inverse cosecant, inverse secant, or inverse cotangent. So I'd like to reciprocate both sides of this function. I like to flip both sides upside down and get tangent. But then by getting tangent, we're going to get 1 over square root of 3, which is the same thing as square root of 3 over 3 when rationalized. Okay, so we have tangent of 2 theta minus pi over 3 equals square root of 3 over 3, flipping it upside down. Now let's take inverse tangent of both sides. So we have 2 theta minus pi over 3 is equal to inverse tangent of square root of 3 over 3. Now, that's a positive ratio with a reference angle of either 30 degrees, or if it's in radians, that'd be pi over 6. But notice tangent is positive in both quadrant 1 and quadrant 3. So we need 2 angles. So we're going to need the pi over 6 and the 7 pi over 6 angle. Now, there's something very special about this problem. Because we have a 2 theta, I think that we could imagine that if we answer right now only between angles of 0 to 2 pi, these would sort of be the fine angles to put down for inverse tangent. But because eventually we're going to divide by 2, anything up to 4 pi, in other words, 2 full revolutions, might end up being wound back, in other words, divided by 2, such that we're going to end up with maybe there's more angles we need to include. So what I'm trying to say is that when we also consider other tangent angles, let's consider some other angles on each end that also might be coterminal angles with these, but then after the adding the pi over 3 and the dividing by 2, they might still fall between 0 and 2 pi. What I'm trying to say is that negative 5 pi over 6, which is coterminal to 7 pi over 6, but a negative rotation, and 13 pi over 6, which is the exact same thing as pi over 6, coterminal, but it's 2 pi plus pi over 6, because it's 12 pi over 6 plus pi over 6, or 19 pi over 6, because that's 12 pi over 6 plus 7 pi over 6. Those angles could work, maybe, because when we divide by 2, they might end up shrinking down so that they'd actually be in the range 0 to 2 pi. So let's not exclude any of these, at least to this point. By the way, on each end of the commas, I'm going to put the little ellipsis here because maybe there might even be other coterminal angles. But let's go ahead and at least work with these 5. So let's add pi over 3 to all of these. Now, by the way, adding pi over 3 is the same thing as adding 2 pi over 6. So if we add 2 pi over 6 to all these angles, what does that look like? So we have negative 3 pi over 6, 3 pi over 6, 9 pi over 6, 15 pi over 6, 21 pi over 6. Now notice though, each of those has at least like a 2 factor in them that could be divided out. So let's do that, greatest common factors. So each of these has a factor of 3 for the greatest common factor. They're all divisible by 3. So dividing all those numerators and denominators by 3, we get negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Finally, what we can do is we can divide all of these by 2 to get the angle theta finally. So dividing these all by 2 basically makes all those 2 denominators into 4s. So we've got negative pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now notice if we had done one more coterminal angle, that'd be a little bit past 7 pi over 4, that'd be a little bit past 2 pi. So that means these 4 angles, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, should be our answers. So let's check on the choices. And indeed, this first answer choice is what we need. Hope that makes sense. Let's move on. Hey, thanks for checking out High Peak Education today. Would you do us a favor and like, subscribe, comment, and share this video? It really helps us to grow the channel, extend our reach, and it helps us to make more content like this to help you even more. Thanks for your support. Hope you're enjoying it. Let's get back to the video. Okay, so for number 16, given triangle ABC with alpha equal to 51 degrees, A equal to 375, and C equal to 452, which statement is true? So 2 possible triangles, 1 triangle, 2 possible triangles, 1 possible triangle, and these have different values for certain angles for the 2 versus the 1 triangle and different B values, or not enough information. This is side-side angle. This is a triangle that is not a right triangle necessarily, and it's the so-called ambiguous case, the law of sines. How do I know that? Because we have an angle across from one side, we only have access to one angle, and it's possible that we might have more than one triangle, or maybe even no triangle, or something like that. Let's write down the formulas of what SSA, side angle, for this possible ambiguous case looks like. Okay, so here's what the ambiguous case formulas look like. Notice the key is we have to calculate this h. So h is the height of the triangle that either could be formed or is formed. This alpha here is the same thing as what my formulas down here are calling angle capital A. And then side length lowercase a is across from capital A, and then lowercase c is also known. So lowercase c is the other known side. Notice that by calculating h, we will figure out which condition we fall into. Now, h is the height of this triangle, thinking about trigonometry. So this height can be thought of as this side of this right triangle. And notice that if the angle A is known, or in this case alpha, and the hypotenuse is known of this right triangle, then you could say sine of this angle is h over c, or you could say h, the height, is equal to c sine of the angle. Okay, so h equals c sine A or c sine alpha, whichever you prefer. Let's go ahead and calculate that because we're going to need that to know which of the conditions we're in. Okay, so h equals 452 sine 51 degrees. Okay, making sure my calculator is back in degree mode. Let's go 452 times the sine of 51 degrees. So we get 351.27. What we can tell is that that number, h, is it smaller than lowercase a? Turns out it is. Is it smaller than lowercase c? Yes, it is. If h is larger than a, which it's not, there'd be no triangle. If h and a were the same, it'd be a right triangle. That's not true. But a, in this case, which is the side across from the known angle, is not larger than c. So it's not just one obtuse triangle. So it turns out we are going to have 2 triangles. 2 triangles are possible. So this is the so-called ambiguous case. The choices we can eliminate are this. It's either 2 possible triangles or not enough information to solve. Now, let's see what's going to happen for B or gamma. Now, if you think about it, gamma is going to be the angle associated across from side length C, And then if you think about it, B is going to be found two different ways. That's like saying from this diagram, do you see that bottom side right here, B, is going to have two different possible values. It's going to have B1 and B2. Notice B1 and B2 are going to have different lengths. So we don't know yet what one of the values of B is, and we don't know if one of the values of C, the angle here, is this or this. Now notice, we're going to get two triangles. One of them is probably going to have an obtuse angle. Do you see that? So it's very possible gamma could equal to this number, and it's very possible B could equal to this number. But we got to work those out. So we have to work out the law of sines, and we have to work it out both ways. So let's go ahead and find angle gamma first, but then let's find both possible values of the angle gamma, which are across from angle C. Okay, so from the law of sines, we see sine of alpha over A is equal to sine of gamma over C. So let's go ahead and put the numbers in. Okay, and then let's cross multiply, putting in 51 degrees, 375, gamma, and 452. Okay, so we have 452 sine 51 is equal to 375 sine gamma. We have to divide by 375 and then take the inverse sine. Okay, so we get gamma is equal to inverse sine of 452 sine 51 degrees over 375. Now remember, because it's a positive ratio, it can occur in quadrant 1 and 2. So that means we're going to get an acute and an obtuse angle for gamma. So let's find each of those. So we're going to have gamma 1 and gamma 2. Okay, so from the scientific calculator, let's do inverse sine, and let's do a fraction. Let's do 452 sine of 51 degrees, making sure we're in degree mode, divide by 375, put the parenthesis over here, close it off. We get about 69.5 degrees. Okay, that's one of the values for gamma. But how about the other value for gamma? That's going to be 180 degrees minus 69.5 degrees. So subtracting these 180 minus the 69.5 degrees we have there, it's about 110.5 degrees. So notice now we have our two values of gamma. It doesn't look like gamma is going to be exactly this number. So I'm going to cross out this. I'm really hopeful that one of the values of B is 153.2, but let's find out, because it could either be B1 or B2. Let's go ahead and finish the calculation with the law of sines using the fact that we're going to get two values of beta, which is the angle across from B, and thus we can calculate B. Okay, so with these values written down, we're going to need to subtract from 180 degrees alpha, gamma 1 to get beta 1, and then alpha and gamma 2 to get beta 2. Let's go ahead and put the numbers in for each of these betas. Okay, so we have 180 minus 51 degrees minus 69.5 degrees, and then 180 minus 51 degrees minus 110.5 degrees. Okay, so from those two calculations, we get 59.5 and 18.5. So those are our two values of beta, beta 1 and beta 2 respectively. So we're going to do the law of sines one more time, but this time we're going to allow for beta to be either 59.5 or 18.5. So we're going to get a formula for side length B, but we're going to plug in beta 1 once and then beta 2 the other time. So let's solve this for B by cross multiplying. So that's B sine alpha equals A sine beta. Let's divide by sine alpha. We just need to plug in the two different values of beta because A and alpha are known. Okay, so we have the numbers plugged in. Let's go ahead and do each of these calculations. So let's do 375 times the sine of 59.5 degrees divided by the sine of 51 degrees. And then let's repeat the calculation. I'm going to go arrow up, and then it's going to be 375 times the sine of 18.5 degrees divided by, again, the sine of 51 degrees. Okay, so for B1, we get about 415.77. And then for B2, we get about 153.11. So now we have our two full triangles solved for. Now you could take the time to draw these out with nice exact angles and side lengths and that kind of thing. But let's go ahead and look at our answer choices. So look at that. 153.2, is that about what we find for one of these? Yeah, it's pretty darn close, okay? That's not exact, but it's pretty darn close. So I'm going to suggest it is two possible triangles. One of them is about 153.2. Okay, I've got 0.11. It's about the same, 0.2. So this is going to be our correct answer. Now, by the way, for a lot of people, the ambiguous case in trigonometry for the side-side angle situation, where you have side A, side C, and then angle A, or angle alpha, as shown here, is one of the hardest things to solve anything before calculus. Like, for a lot of students I've worked with, this is one of the hardest things to solve. So if this was much for you to take in, don't worry about it. It's just, let me go ahead and just take a second and out loud review it a little bit. So when you have a non-right triangle and you have a side length across from a known angle, and you have the side length in between those two, so that would be side length C. You don't know if you're going to get no triangle, one triangle, that's a right triangle, two triangles, one of which is obtuse, one of which is acute, or an obtuse triangle, one triangle. The way to know that is you got to calculate H. H is the height of the triangle. H comes from the side in between the known side and the angle, that's C, times sine of the known angle, in this case sine of alpha or sine of A. Because that was smaller than either of the two known sides, we are going to get two triangles. That's because at this step, when we take the inverse sine of this positive ratio, 69.5 degrees is the reference angle in quadrant 1, but it's also the reference angle in quadrant 2. Sine has two positive values, so we get ambiguity there. We're going to get two possible triangles, two possible values for gamma 1, gamma 2. From gamma 1, gamma 2, we can find beta 1, beta 2, just from subtracting from 180 degrees. The sum of the interior angles of any triangle should add up to 180 degrees. But then we just need to repeat the law of sines to find side length B. But notice side length B, we calculated in two different ways because we have two different values for beta. Beta being the angle across from side length B. So we get B1 and B2 from calculating from the law of sines. We compare to what we have. We have the correct answer. Hope that makes sense. Again, I feel like there's not a lot of teachers that really can explain the ambiguous case for a non-right triangle using the law of sines. But I hope that's clear. Thank you, and let's go ahead and move on to our next question. Okay, question 17. Which of the following is the graph of y equals 4 cosine 3x minus pi over 4? One suggestion, although not every teacher does it this way, I like to factor out the period modulator, that is the number that multiplies the x being the variable, because I think it's easier to tell what the period is and what the true phase shift is. So I'm going to do that. Okay, so factor out the 3, we have 4 times cosine of 3 factored out, x minus pi over 12. Let's think about why it's pi over 12, because if you multiply the 3 back in, I'd have 3 pi over 12, which is simplified pi over 4. From this, we can tell what the values of the amplitude are, period modulator, and the phase shift. All right, so let's go through each of these one at a time. So the amplitude, that's A, is equal to 4. Hopefully you know what that is. That's the distance from the midline to the max or the midline to the min. In other words, from the average value, what distance does the top or the bottom of the wave go down? From max to min, that's 2 times the amplitude. All right? So it looks like, eyeballing it, most all of these graphs have 4 for the amplitude. So that doesn't really tell us much. So then the period modulator is often called B. Now I'm not referring to graph B necessarily. I'm just saying usually this constant here is called B. B is equal to 3 in this case. To get the period, what we're going to do is we're going to take the typical period of cosine, which is 2 pi, and we're going to divide by the period modulator. So the period's 2 pi over B, which is 2 pi over 3. Now that we have the period, let's go ahead and see if we can tell which of these graphs have a period of 2 pi over 3. Let's go ahead and take a look between, let's say, letter A here. So halfway between pi over 6 and pi over 3. So this would be 3 pi over 12, which would be the same thing as pi over 4. That's because I think each of these increments here is going to be 1/12 of pi. Now, by the way, that actually makes sense because we're pretty soon going to get to twelfths. You could see that each of these graphs has an increment of halfway to pi over 6. So each of these increments is pi over 12. So this is 3 pi over 12. And let's see if we get back to this minimum value. So this is, we can see here, 2 pi over 3. Then this right here would be, so 2 pi over 3 is the same thing as 8 pi over 12. So then 1, 2, 3 more, that'd be 11 pi over 12. Now 11 pi over 12, that's 8 pi over 12 from here, but 8 pi over 12, that simplifies to 2 pi over 3. So that's the correct period. Let's look at this one. So if we go from here, which is pi over 12, to here, now this is pi over 3, that's the same thing as 3 pi over 12, and this right here would be 4 pi over 12. So this would be 4 pi over 12. Now if this is pi over 12 to 4 pi over 12, then that's going to be 3 pi over 12, which is a period of pi over 4. So that's not correct. So B has too high of a frequency, too short of a period. Let's look at this one. This looks like it's a little bit less than pi over 12. And again, this looks like the period's about pi over 3. Do you see that? Because this is just a little bit to the right of pi over 3. This is a little bit to the right of 0. So this is not the right period. So C is also out. Now what about D? This looks like it goes from about pi over 12 to, looks like 2 pi over 3, maybe plus a little bit more. So this seems like it's okay so far. So A and C look like they're okay so far in terms of their amplitude and their period. All right, then let's finally do the last constant. Okay, so the last constant is the phase shift. That's the horizontal shift. We often call that C. And C is going to be pi over 12, translation to the right in this case. So we take the whole graph and we shift it pi over 12 to the right. Now, if you recall, a cosine function is going to typically start at its maximum value. Just going to start up on the top of the y-axis when it goes through one full phase. So we got to look for something that got shifted over pi over 12 units from its maximum value. So this looks possible because that looks like it's about pi over 12 shifted to the right. What about this one? It got shifted to the left. See, the maximum value got shifted to the left. So A is not correct. So D for the correct answer. They all have the same correct amplitude. B and C were too high frequency, too small of a period. A and D had the correct amplitude and period, but only D was shifted to the right for a cosine. Okay, I hope that makes sense. Let's move on. For number 18, one day, a long time ago, a farmer traveled 40 miles to see the county's prettiest barn. Being mathematically minded, he found the height of the barn by picking a point along level ground, which was 135 feet from a point on the ground directly below the top of the barn, and then measured the angle between the ground and the line of sight to the top of the barn to be 41 degrees. To the nearest foot, what is the height of the barn? Now, I pulled this diagram somewhat randomly from a textbook source, but hopefully you get the idea. Like, we don't really care how tall the person is. We just want to know how tall is the barn. The height of the barn, let's ignore the height of the person. Let's assume the barn is a lot higher than the person is. So when we're looking for the height of the barn, we're looking for the height of the barn above the person's line of sight, above like their eye level. We don't really care about the 40 miles we traveled. We are on level ground. We're 135 feet away. So I'm going to label that as this horizontal distance. From a point on the ground directly below the barn. And then the angle is 41 degrees. So we want to know what this delta y is. So delta y would come from the tangent function because it'd be opposite over adjacent. Tangent of theta is going to be like delta y over delta x because delta y is the height. Delta x is this horizontal distance the farmer is away from the barn. We can multiply by delta x and then put the numbers in, get delta y. Okay, so we have our formula. Delta x tan theta equals delta y. Let's put the numbers in. It's 135 feet times the tangent of 41 degrees. So making sure our scientific calculator is in degree mode, let's do 135 times the tangent of 41 degrees to get our answer. 117.35. And that's feet. So we see this fourth answer choice down, 117 feet. That's going to be our correct answer. Hope that makes sense. Let's move on. Okay, so for number 19, determine M such that the two vectors C and D are orthogonal. Now, vector C is 2m minus 4. D is 5, 6. Now, hopefully you know we can say when we take the dot product of two vectors, that should be 0 if they were orthogonal. Orthogonal means they're exactly 90 degrees from one another. They're perpendicular. They meet at a 90-degree angle. This is essentially how the law of cosines is also more or less derived. If we do the dot product between these two, again, we want the dot product to be 0. So let's go ahead and start doing this with these vectors. Okay, so let's take the dot product of these. Now remember, the dot product, you get to multiply the x components, multiply the y components correspondingly each, and then add them. 5 times 2m is 10m. Negative 4 times 6 is negative 24. Add them up, equal to 0. So that's pretty straightforward. That's just going to be 10m equals 24, adding 24 to both sides. Divide by 10. It's like moving the decimal place 1 to the left. M equals 2.4. So we have our correct answer for m to make sure that the dot product is indeed 0. The vectors are orthogonal. There's also a formula which shows us the cosine of the angle between the two vectors from dot product. But it turns out it has to be cosine of 90 degrees. That's because cosine of 90 degrees is 0. So it all would be the same final result. All right, I hope that makes sense. For number 19, let's move on to our last question. Okay, so for question 20, it says find the exact value of secant theta if theta is in standard position and the terminal side of theta is in quadrant 2 and parallel to the line 8x plus y equals 4. Okay, so this is not an algebra class. Let's figure out what the slope of this line is so we can figure out what the slope of the terminal side is. So this line is in standard form, so the slope in standard form is negative a over b, which is this front coefficient, and then this coefficient is b, so it's negative 8 over 1, so that's negative 8. So a line with a slope of negative 8, what that means is it's going to be in quadrant 2 going through the origin, and we know its slope is going to be negative 8. So it's going to be highly sloped like this. It's going to rise negative 8 and run 1. So what that means is in quadrant 2, you could imagine this opposite side is going to be 8, and this side right here is negative 1. So this is basically our right triangle. So that means y is equal to 8, and then x is equal to negative 1. Now, what about the hypotenuse? We can simply use the Pythagorean theorem. We can simply use the Pythagorean theorem that r, which is the hypotenuse, is the square root of x squared plus y squared square rooted. So from this, that's going to be negative 1 squared plus 8 squared square rooted. So that's going to be the square root of 1 plus 64. So that's the square root of 65. Now in trigonometry, we typically don't assume that r is a negative, it's a positive radius. So what we're going to do is we're just going to have it as square root of 65. So we want the exact value of secant theta. So secant theta is the reciprocal of cosine. So it's going to be hypotenuse over adjacent. In other words, r over x. So that's going to be square root of 65 over negative 1, which is the square root of negative 65. So that is our final answer for number 20. Great job in getting through this trigonometry exam. If you've hung with me the whole time, thanks so much. Thank you very much for watching High Peak Education. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Social media links are down in our description below. Please support us and share this amongst your social networks. Thank you very much for watching. I will see you in the next video.